Welcome to this lecture series in real analysis. In this lecture, we'll show that if a sequence of functions converges uniformly to a function f, and if each individual member of the sequence is continuous, then the limit function is also continuous. Okay. Here are two problems for practice. And now let us get started. So as I said in the intro, I just want to prove that if a sequence of functions converges uniformly to a function f, then the function f is continuous provided the elements of the sequence, the functions in the sequence are also continuous. I will give a full formal proof, but on this one I would suggest, in fact I would suggest this for every theorem, that you should try it for yourself before looking at my exposition or any exposition for that matter. But on this one, I'm going to deliver a dry and boring lecture, more or less. So you will get a lot out of this opportunity if you try to prove the theorem yourself rather than just passively witness the proofs that I'm going to present. Anyway, I have to do it. So first we will prove a preparatory lemma. So we start with a uniformly convergent sequence of functions defined on a set S of reals. Suppose X is an accumulation point of the set S. And suppose for each n, the limit, this limit exists and whatever that limit is, we are calling it capital A-N. Suppose this exists and we are calling it capital A-N for each n, then this sequence is convergent. So if you start with a uniformly convergent sequence of functions and you pick any accumulation point so that one can actually talk about this, and then if each of these limits exist, then we are trying to say that this sequence converges. Technical looking statement, but it will be very useful in the next slide. Let me give a proof. Okay, so fix epsilon greater than 0 and we will prove the convergence of this sequence by the means of Cauchy's criterion for convergence. Okay, so fix some epsilon greater than 0, and since this converges uniformly, by Cauchy's criterion for uniform convergence, we have by Cauchy's criterion for uniform convergence that there is some natural number n such that whenever we choose m and n at least capital N, and we choose any element of the domain, we find that the function values corresponding to the indices m and n at the point t is controlled by epsilon by 2, we will write. Right, immediate from the Cauchy's criterion for uniform convergence. Okay, which implies as t approaches x, we get this. Why can we take the limit? Simply because each of these limits exist. That's the hypothesis. So therefore the limit of this thing also exists as we take t going to x. Okay, and this strict inequality will convert into a possibly not strict inequality. That's fine. So this implies, since the limit will be pushed inside, the absolute value function is a continuous function, so the limit will be pushed inside. I will not skip a step and write the full thing. Which implies that, okay, which is in particular less than epsilon. So for cultural reasons, we are writing less than epsilon. So this shows that the Cauchy's criterion for convergence holds for this sequence, and that's it. That proves this preparatory lemma. Very simple, straightforward proof. And now let's proceed. So this is the key lemma. This is the lemma about interchanging limits. So if you recall the obstruction which forbade us.
Sorry, I can't make a phone call with your iPad.
So the obstruction which forbade us from proving or deducing the continuity of the limit function from the continuity of the sequence of functions, where we only assumed pointwise convergence, was an issue about interchanging limits. So this lemma shows that if you assume a stronger notion of convergence, namely uniform convergence, then the issue of interchanging limits vanishes. So what is this precise statement? You start with a sequence of functions, assume that sequence of functions converges uniformly to some function f, and fix an accumulation point of the domain. And like in the previous lemma, assume that this limit exists for each n, and we will call this an, like in the previous page. So assume this exists and we'll call this an. So then we are claiming that this limit also exists, and this interchanging limit business can be carried out. Okay. So this limit is same as that limit, that thing, right? Because this is precisely f of t, right? The sequence of functions converges uniformly to the function f, and hence in particular pointwise. So this is nothing but f of t, and we are saying that this limit exists and is equal to that, which is really a statement about interchanging limits. And once we do this, the desired statement about the continuity of f provided each of these are continuous will also follow. That will be like a one-liner, but anyway, so let's prove this. This is the main result. Okay. So by the previous lemma, this sequence is convergent. This sequence is convergent, and let's say A is its limit. Great. What do we want to do? We want to show that. Maybe I'll choose another fancy color. Want to show that limit t tends to x ft is limit n tends to infinity. Right? That's exactly our aim. That's exactly the statement that we want to prove. As I said, this is nothing but f of t. So this left side is precisely that left side. And this is what I've written here. But what is this? This is capital AN, which by definition of capital A is equal to capital A. So this is what we want to do. Upshot is we want to prove this equality. Okay, so fix epsilon greater than 0. Then this difference, this is what we want to estimate if t approaches x. So this difference we will break into 3 parts. So by triangle inequality, I'm directly writing by triangle inequality, this is estimated by right? This is immediate from triangle inequality. These terms kind of are the extraneous dummy terms, but breaking this difference in this way helps us estimate. So now, since this convergence is uniform and since capital N converges to A, there is some capital N such that whenever we choose little n larger than that, or at least that, and we choose any point in the domain, because of uniform convergence, we can choose any point in the domain and still we will have the following two estimates. We will estimate by epsilon by 3, and the same for the other one. So what are you doing? Because of this uniform convergence, we had this much. There was some capital N such that this holds. And because of this, there was some capital N such that this holds. But we can just choose the bigger of those two capital N's and write the single statement without cluttering things. That's all. Okay. So here we are. And now we get, by our previous triangle inequality thing, we can write a particular, so I should have explained. So when we did this estimate, we could have chosen any little n we wanted. Right here, the little n is on us. We could have chosen 1, we could have chosen 1 billion. So now, since that we have located this capital N, which will allow us to say that this is small and that is small, we will choose that capital N in place of little n. So by the thing, we have this, but this is at most epsilon by 3, and that is also at most epsilon by 3. So that gives correct, which is right. And what did we want to do again? We wanted to say that if t approaches x, then this thing is at most epsilon. That's what we wanted to do. Now, note that by definition of a sub capital N, this difference, by definition of a sub capital N, as t approaches x, this thing becomes equal to a sub capital N. Right? That's the definition. So as t approaches x, this thing can be made arbitrarily small, and therefore so can this be. And that is where the proof ends. But just to write one line to be completely formal, you can take the lim sup if you like. Let's just take the limit. Why take? We could have just taken the limit, but then one could object that how do we even know that this limit exists when t approaches x? So therefore, let's take lim sup to not have any pesky objections. So we'll just take lim sup t approaches x to epsilon by 3 plus lim sup. Right, but we know that here the limit exists. The limit of this as t approaches x is 0. So this lim sup is actually limit, and it actually is 0. So we can just erase it, and that's it. So what we've shown is that the lim sup of this quantity can be made as small as possible. The lim inf is certainly non-negative because this is a non-negative quantity. So with that, I just leave it here for you to finish. It's nothing. That this is 0, and that finishes the proof of this lemma. Right. So there was only one key step, which was about the splitting. Such an argument is called a 3 epsilon argument because you get 3 different estimates in epsilons. Okay, and now let's finish the main business. Finally, if we have any subset of real numbers, we have a sequence of continuous functions converging uniformly to some function f, then the limit function is also continuous. This is the song that we have been singing, and now we will finally write the lyrics of it. So to show continuity, fix any accumulation point of S, and what we want to do is want to show that of course. So what I should say is the following. Let X in S. I'll explain why am I fussing about this. Fix a point in the set S. If it is an isolated point, nothing to do. So let's assume that it is an accumulation point. So this be an accumulation point of S. So pick an accumulation point of S which is in S. Because if it is not an accumulation point, then it is an isolated point. And for isolated points, there is nothing to do. So what we want to show that is limit t approaches x, ft is equal to fx. Since x is in S, we can actually write this. This is why I kind of glitched a little bit. Okay, great. Now, by continuity of fn for each n, we have this limit exists and is equal to fnx because fn is continuous, and therefore by the previous lemma, in the notation of the previous and previous to previous lemma, this is just an. Okay, so anyway, so now by the previous lemma, the previous lemma was about interchanging limits, which read as follows. Right? Which implies that this thing is equal to that, as we commented here, and this is equal to that because fn in particular pointwise converges to f. So we have this equality. Great. But finally, this is equal to f of t. Sorry, this is equal to, what have I written? This is x. This is equal to f of x. Right? This thing is equal to that. I had erroneously written a t here, but it's an x. And this limit is equal to f of x because, again, this is a pointwise convergent sequence in particular. So this is what we wanted to show, and we are done. So this was a very simple proof once the previous lemma was settled. Alright, so with that I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.